Welcome back. We're looking at the final page through number 26 that I'm going to review tonight, which consists mostly of solubility. Since I left the last video off talking about like dissolves like, let me skip to number 25 and do this real quickly. A polar solvent, something like water, will dissolve a polar solute, so it would be soluble. It would dissolve anything that is ionic, like salt in that last example, because of those electric charges and the dipole of the polar solvent. So, soluble. The nonpolar solute, which does not exhibit very strong dipole forces, just a little bit of dispersion forces, those temporary dipoles, would be insoluble because it would prefer to associate with itself. The nonpolar solvent will not dissolve the polar solute or the ionic solute because, again, these prefer to interact with each other because of dipoles, which nonpolar solvents do not exhibit. Permanent dipoles, at any rate. The nonpolar solute will dissolve in the nonpolar solvent. Like dissolves like. Alright, moving up for 18 through 24, you actually need to refer back to the graphs on the previous page. So you can see those right here. I'll be pulling this back and forth for these different problems. Alright, what mass of potassium nitrate will dissolve in 100 grams of water at 50 degrees Celsius? Since it's out of 100 grams of water and the axes on solubility graphs are out of 100 grams of water, I can safely ignore that mass of water for this problem. Instead, just look at the 50 degrees Celsius. Alright, we're looking for potassium nitrate. It's a solid, so we're looking at this graph over here. And this is the solubility curve for potassium nitrate. Remember, the line represents saturation, above the line, supersaturation, below the line, unsaturation. So let's find 50 degrees, and we'll make a little dotted line up here until it intersects potassium nitrate, and then I'll do the same thing to the y-axis. My lines are a little bit crooked, but that's okay. We're just going to estimate this. This appears at 50 degrees to hold about 70 grams of potassium nitrate. If you look and get slightly different values, that's okay, because this is a small graph. We're just eyeball estimating here of some hand-drawn lines. So as long as you're close to 70, you're good. If you're something outrageous like 80 grams, which is way up here, then you would be very wrong. But remember, the test is a multiple choice test. They're not going to give things that are nitpickingly close together if you're estimating. Second one. What mass of potassium bromide will dissolve in 100 grams of water? Again, we can just ignore this extraneous information. At 50 degrees Celsius. So potassium bromide, this line. I'll just extend my 50 line up a little smidgen, and then draw another set of lines out over here. Looks to be about 80 grams of potassium bromide. Alright, 25 grams of potassium nitrate is dissolved into 100 grams of water. Again, will be extraneous because that's the units on the graph. At 30 degrees Celsius, is the solution saturated, unsaturated, or supersaturated? So we're looking, is it on the line, below the line, or above the line? So, first thing, 30 degrees Celsius. Let's extend a line up from that. Well, let's make this a solid line. Make it a little different. Oops, I think I just overshot what we're looking for again. Potassium nitrate. Yes, I overshot. So potassium nitrate, doesn't matter. We'll go where it intersects potassium nitrate and draw a line over to our temperature axis. It's just a smidgen shy of 40. So about 40 grams could dissolve at 30 degrees Celsius. If we only have 25 grams, we could still dissolve another 15 grams. Because we could still dissolve, it is unsaturated. Okay, if we did this graphically, the 25 would be somewhere around here, and go over to 30, we are right here. We could dissolve from here all the way up to here. Okay, from this part to that part. So yes, we could dissolve more, so it is an unsaturated solution. Let me erase some of these lines so we can continue on. Alright. In order to make the solution saturated, how much more potassium nitrate must be added? Well, I kind of already answered that in the last question, but let's just go ahead and do it graphically here. We could dissolve 40 grams, we said. We only had 25 grams, therefore, just writing the wrong number, an extra 15 grams could be dissolved before it became saturated. What is the minimum mass of water to dissolve 30 grams of potassium nitrate at 30 degrees Celsius? Alright, now we're going to be looking at the mass of water, which we've been previously ignoring because it was the definition of the axis. So first of all, let's go and find potassium nitrate and 30 degrees Celsius. Okay, 30 degrees Celsius, extend a line up. Alright, potassium nitrate, extend it over, and this is what we said was about 40, maybe a little bit less. I'll just round it to 40. So if we can dissolve 40 grams at 30 degrees Celsius, we want to know the minimum mass of water to dissolve 30 grams. Alright, so this is 40 grams out of 100 grams of water. How little water could I use to hold 30 grams? Okay, we've got a simple proportion here. So we'll do a little cross multiplication and divide and find out 75 milliliters is the smallest value possible to dissolve 30 grams of potassium nitrate. Alright, what mass of oxygen can be dissolved in 1,000 grams of water at 30 degrees Celsius and at 20 degrees Celsius? 1,000 is definitely not 100, so we cannot ignore this anymore. But we'll take it as we get to it. Starting with 30 degrees Celsius. Oxygen is a gas, so we're going to look at the graph that curves down, because gases become less soluble as the temperature increases. Just think about soda. And here's the oxygen line. So 30 degrees Celsius, extend it up and over. And this concentration is in grams per 100 grams, so this is about 0.003 grams of oxygen. Alright, so if 0.003 grams of oxygen will dissolve in 100 grams, we want to know how many grams of oxygen will dissolve in 1,000 grams. So 10 times as much will be 0.03 grams of oxygen. Okay. Notice we cannot ignore that 1,000. It's just another proportion. Cross multiply. 1, 2, 3. Divide. 1, 2. 0.03. Our final answer. At 20 degrees Celsius, so return to the graph. Draw an arrow, not an arrow, a line up from 20. Notice there's more solubility. Extend it over. It is in between 0.003 and 0.004, so let's call this 0.0035 grams per 100 grams. Whoops, started to write that under the wrong problem. Because we were doing out of 1,000 grams. Again, we set up a proportion, cross multiply, divide, and we wind up moving the decimal over by 1.035 grams. Oops, off the screen. There we go. 0.035 grams. What mass of oxygen can be dissolved in 100 grams of water at 20 degrees Celsius? Well, look at this. We already have this one answered. 0.0035 grams. Because that was what we looked up and found on the graph. Real quick definitions for number 26. An element is the simplest form of, matter, which retains all properties of that element. So if you had a block of gold, you could divide, I'm sorry, I'm not on the screen. There we go. Zoom out a little bit. You could divide that block of gold up until you reached the atomic level, and that would be your element. Okay? Single atom. Type of atom. It's obviously not just one atom of gold in the universe. Cation. Positive ion. It is formed by loss of electrons. Anion. Negative ion. Gain of electrons. Ionic compound is a compound formed by electric attraction of cations and anions. Simplest ionic compounds are between metals and nonmetals, but of course there's polyatomic ions, and that introduces a slew of permutations of possibilities. So, electric attraction between a cation and an anion, or plural thereof. Covalent compound formed by the sharing of valence electrons. And this occurs between non-metals. Okay? And tune in for their... Oh, never mind. That was the last video for tonight. See you guys tomorrow.